Cool. Okay. So I think, yeah.
And you
All right.
should
Can
be able to
everyone see
hit,
that?
yeah, you should be able to hit like the presentation view too to get rid of that top bar, but it's not the end of
All
the
right.
world, but just um,
Yeah, let's see. Oh, this full screen, entire screen. There we go.
yeah, there, that's the ticket. All right.
Okay. Yeah. Sorry for those technical difficulties there.
Oh no,
Um,
not at all, not at all. All right, well we're at time, so I guess I'll just go ahead and say yeah, so I when I was casting about for a roster for this second run of the workshop, um I talked to Father Joseph Sellinger, and he alerted me that there had been a conference at Chapman with some interesting talks, which I hadn't known about. And so, anyway, I went and took a look at those and came across Jonathan's really interesting talk and thought it would be a good fit for our audience. So I asked him to if he'd be willing to give it again, and he graciously said yes. So thank you very much, Jonathan, for doing that on short notice, and thanks you for giving up kind of your whole day. You've been here all day, so that's really generous of you. Much appreciated. So
and of
anyway,
course, thanks.
Jonathan, take it
Yeah,
away.
thanks very much, Ryan, for inviting me. And thank you for everyone who have braved the entire day, who's stuck it out to the end. I sense there's probably, some fatigue. I share the fatigue, so I apologize on any occasion in which I stumble over my words. And I'll try to be as animated and intellectually stimulating as possible. So we'll see how that goes. I'll also try my best to read as much as possible from the slides. That will reduce the danger of my going over time or anything like that. Failing to get to some substantial material, I tend to accidentally go on tangents and then start running out of time. So the title of this paper is Aristotelian Geometrical Monism. So it's sort of a paper that has some historical theses, some novel interpretive theses on Aristotelian geometrical ontology. And it also dovetails with some discussions in contemporary analytic philosophy of mathematics, so in particular debates over mathematical pluralism. So the claim is that if you have certain metaphysical commitments in your mathematical ontology, and in particular your geometrical ontology, this might have some import to settling certain questions in the questions of mathematical pluralism. And in fact, extended from that, there might be certain things that settle certain facts about your geometrical ontology that then will also settle certain questions in the debates over mathematical pluralism. In the case of Aristotle, this interesting historical case, the argument is that it's actually kinematic facts, so facts about kinematic finitism, that in fact will settle these questions. So it's sort of this interesting case in which you might think that, as I should start saying, you might think that for mathematical propositions, particularly of a pure mathematical variety, that these are going to be alethically insulated from discipline extraneous facts. So you might think that these mathematical facts are not going to be the sorts of things that are settled by facts in other disciplines, particularly disciplines like kinematics or astronomy or something like this. But if you have certain metaphysical commitments about what the necessary conditions are for geometrical propositions having geometrical content, then you might actually have this sort of position. You might be a sort of thoroughgoing Quinian and confirmation holist, and then you might think that, of course, with minimal mutilation, there's never anything, including geometrical propositions, logical propositions, that's off limits for revision on the sort of confirmation holism. But most people don't have this particular position. Most people are not austere Quinians in that sense. Okay. So on the dominant contemporary conception, geometries are pure mathematical theories with truth conditions independent of the de facto curvature structure of the world, and let alone its absolute metrical properties. So when the geometer is doing geometry, they don't care about whether or not we're living in a de Sitter or anti-de Sitter or flat space, or what the global topology is, or whether or not general relativity posits pseudo-Riemannian manifolds in 4 dimensions. What they care about is, sort of what's internal to the geometrical theory. So if they're working in an Euclidean geometrical context in 3 dimensions, then that's what they care about. They're working in the object theory. And the same thing if you're working in a Lobachevskian or elliptical geometry, or in a pseudo-Riemannian or Lorentzian geometry. Okay, so even on an Aristotelian conception, geometry is the science of natural objects in quantum, He, insofar as He is that reduplicative operator. We'll talk about that a lot. They are continuous and quantitative. Thus, the domain over which geometry theoretically legislates is just, in one sense, the range of possible physical objects themselves, but abstracted from their absolute metrical properties, including the metrical properties of the cosmos in which they're embedded. So you might ask this question, what are absolute metrical properties? These are metrical properties that don't just consist in relations to other perceptible or abstracted magnitudes. In our best physical theories, like in general relativity, what we posit is 4 dimensional pseudo-Riemannian manifolds, and these have intrinsic sort of metrics. So there's this intrinsic metric on the space-time manifold, and that's something that doesn't just consist in a certain relation between physical objects. So if you have this sort of view, but you're also an Aristotelian, you're going to think that in general, geometry is not going to be such that when you abstract from certain perceptual magnitudes, you also inherit the absolute metrical properties of those magnitudes. Okay. Despite this, I infer and evaluate what I argue is exactly this rather surprising corollary of Aristotle's finitism concerning locomotive kinesis, this change or movement, given his astronomy and conception of geometry, that geometrical monism is true. In particular, the uniquely true geometry on Aristotle's astronomical assumptions is in fact a kind of Euclidean geometry. I've spoken a lot with Marco Panza, who is at Chapman. He's a good philosopher and historian of mathematics. So I'll also try to answer this question that he finds at least as interesting, which is whether Aristotle, in virtue of these considerations, is also committed to his geometry being Archimedean in the technical sense of that term. Um, so I would argue that he is. There are interpretations of this particularly controversial passage in the Physics Gamma, which I'll discuss, on which he's neither Euclidean nor Archimedean. So we'll discuss this. So we shall see that this is an unappreciated consequence of Aristotle's attempt to reconcile his finitism with geometrical practice. So as Ryan had said, I first presented this paper at this conference on mathematical practice. So there's an emphasis on Aristotelian finitism and how it interacts with the infinitary sort of mathematical reasoning of his day. So I can talk a little bit about that more generally. There are a few possibly problematic propositions, say just in book one, 112 or 122. And then certainly once you get to conics and conic surfaces and sections with Apollonius, then there are more problems that arise for finitism. But Aristotle is alive to these issues. And in fact, he criticizes the Democritean sort of philosophy of mathematics, which he says is unable to accommodate or countenance the standard mathematical practice of the day. So this is a really central desideratum for his theory of mathematical ontology, as he thinks that it's very important that at least with some sort of suitable paraphrase or interpretation, he can countenance with his geometrical ontology the kinds of geometrical practices of the geometers of his day. Okay. So yeah, this might sound incredible. Again, these geometrical theories are individuated by their respective collections of axioms, and so you might think that just fixing on a logic, there's nothing more to say about whether or not a geometry is true relative to other geometries, except something like it's instantiated by the physical structure of the world. And if you have that sort of view and you don't want to give up general relativity, then you're going to have to say something like, well, the uniquely true geometry, the maximal geometry, is going to be the geometry of four-dimensional pseudo-Brownian manifolds. And that's very weak geometry. You won't be able to prove very much in that. In particular, because if you have any curvature in that space, which is not flat, then you're not going to have, say, even like the triangle postulate. You won't even have that the interior angles of a triangle sum to two right angles. You certainly won't have the parallel postulate. So likewise, once geometries are distinguished, there's a little more to they're being true, you might think, than just whether or not they are in fact realized in the spacetime manifold. So you might think that on this line of reasoning, the very possibility of distinguishing between geometrical theories, where you just think of geometrical theories as differing collections of axioms that result in differing sets when you close them under entailment within a suitable logic or a suitable system of construction procedures, admissible construction procedures, just entails this, that there is no sense to be made in claiming that one geometry is true relative to other ones. It doesn't make sense to say that Euclidean geometry is true. It has genuine geometrical content, whereas Lobachevskian geometry doesn't. So part of the motivation for this paper is to reveal that this reasoning above presupposes non-trivial substantial conceptions of geometry, geometrical reasoning, and mathematical ontology, which themselves enjoy a prima facie plausibility contingent in particular to our current mathematical philosophical way of thinking. So it's not to defend geometrical monism or to motivate geometrical monism per se, but it's to use this interesting case study of Aristotle and to say if you have particular conceptions of geometrical ontology, then the motivations for mathematical pluralism, geometrical pluralism that you have here, in fact, don't go through. They manifestly are false. So this is not to say that our contemporary conception of pure mathematical theories and abstraction from worldly structures are misguided, right? So a lot of my work is in mathematical logic, so I do a lot of work with these sorts of purely syntactic structures, maybe with intended models or something like that. So I'm not trying to criticize that methodology or anything like that. But there might be something to be said about there being sort of syntactically geometrical theories, and then geometrical theories that have genuine substantial geometrical content. And that's one of the questions that's explored here. Okay, so we do this by examining Aristotelian geometry. Okay, so I should just say, as a mathematical logician, I'm definitely live to how the way I put things won't be fully rigorous or anything like that. And trying to put these things in a fully rigorous way would extend beyond what's strictly determined by the text, by the textual evidence. So I'm going to try to stick within the textual evidence. So that's just to say that I'm going to argue that there is an important sense in which Aristotle, in virtue of his kinematic and astronomical commitments, is committed to the only geometry having genuine geometrical content, being a Euclidean kind of geometry. That's not to say that I'm introducing some new axioms or am claiming that he endorses some extension of absolute geometry that you see in Euclid, maybe with the fixes with intersection and Pasch's axiom. Nor am I saying something about the meta theory necessarily. But roughly what I'm going to argue is that he has this meta-theoretic commitment that he introduces in order to reconcile his geometrical ontology with the mathematical practice of the day, that amounts to saying that if you have a geometrical configuration that has genuine geometrical content, it's in the science of geometry, then there are going to be other configurations of the same type that also have genuine geometrical content in that sense. Okay. So in this paper, then, I'm going to clarify Aristotle's ontology of geometrical objects. So I'll go do a little bit more work than some of the previous talks, which didn't focus on this, on geometrical abstraction for Aristotle, aphoresis. And then I'm going to overview, this will be a review for, I think, most everyone, Aristotelian astronomy and how modulo some analytic reasoning entails finitism about perceptual magnitudes. A little bit of this is relevant to Martina's talk, so maybe I'll email her about it. I guess it's like very late in the UK now. Then I'm going to argue that Aristotle is committed to the uniform possibility of geometers finding an angle-preserving downscaling of any geometrical configuration and in a common geometrical space. And we know that thanks to Sacchieri and also a pseudo-proof of postulate 5 by John Wallis, that this is equivalent to the parallel postulate. At least like the pseudo-proof is why people wanted to investigate whether or not it was equivalent to the parallel postulate. He didn't prove it was equivalent to the parallel postulate because then it would become manifest that he's begging the question. Okay. So again, I'm not saying that we're extending our system with any common notions or further axioms or new construction procedures or anything like that. Right? I'm not making a positive claim about those things. There are ways to go on each of those accounts, which will be theoretically equivalent to what I'm saying. But these sorts of things will be textually undetermined, in part because some of these distinctions between object theory and meta theory are much later logical distinctions. Yeah, right. So it doesn't make sense to say something like that Aristotle is committed to, textually, to one of these ways of going rather than the others. But there are equivalent ways of going on both of these counts. Okay, so it is by geometrical limitation in virtue of the meta-theoretical commitment rather than an axiom or some construction procedure that Aristotelian finitism about locomotive kinesis is rendered consistent with geometrical practice. Okay, so as I've been highlighting, this is going to highlight underappreciated ways in which positions concerning mathematical ontology can limit mathematical possibility in debates over mathematical pluralism. Okay, so Aristotelian sciences, this should be, I think, review. If you didn't know before today, then after today, this is now review, because many talks have talked about this. So they're roughly going to be proper to respective genera, and geometry, being a special theoretical science, is no exception. So while arithmetic and geometry are both sciences of quantity, posos, they are distinguished by their being sciences of the subgenus number, arithmos, and magnitude, megathos, respectively, of quantity. Now, like the main proof text for this comes from the Metaphysics Delta. There's a different mode of speaking that he gives in the posterior analytics, in which he seems to say that that arithmos is going to be a subgenus of megathos. So that can't be consistent with what he says in the Metaphysics Delta. But the thought is that the Metaphysics Delta, this sort of taxonomy, is the more mature way of spelling out his system, terminologically speaking. So that's the relevant passage. I'll refrain from reading that for the sake of time. So I'm going to follow Aristotle's terminological convention in the metaphysics. So I'm going to understand quantity to be the genus of number and magnitude, which are respectively the genera of the special sciences, arithmetic and geometry, and I'll focus on geometry. So an immediate question that arises in this passage here is whether or not Aristotle is analytically defining geometry to be finitary, because it sounds as though when he's talking about magnitudes, he's talking about magnitudes that are bounded. So he's not just talking about lengths, breadths, and depths, but actually bounded lengths, breadths, and depths. So this is how you get, of course, like lines and surfaces and bodies. So if that's just what the domain of geometry is, then it sounds like it's an analytic truth that, in fact, geometry is a finitary kind of discipline, and that, of course, will have effects on your object theory. But I don't think this is the way that you should interpret these things. I think that right, so this point right here is pulling out the reasoning that I sort of just gave, right? seems like by definition, the mathematical objects in this definition given are limited, right? So it'll be analytic truth that it's a finitary system. But this merely arises from Aristotle's commitment to what he takes to be a demonstrated physical fact that there are not possibly actually infinite lengths, breadths, and depths, since there being such would imply the existence of an actually infinite body, which is physically impossible. And so we'll go into that. Okay. So if the geometer studies possible constructions from, say, lengths and points, then without loss of generality, he can vertically be said to study possible constructions from lines and points. In fact, Aristotle seems to indicate that lengths rather than lines is the proper account of the domain of geometry, even if translators have unfortunately glossed over this particular distinction. And you see the distinction in that particular metaphysics delta passage. Okay, so let's look a little bit about geometrical abstraction. So some magnitudes are going to be perceptible, as they constitute the limits of physical bodies, and indeed Aristotle does not uncommonly use the phrase perceptible magnitude. So while we've clarified that Aristotelian geometry is the special science of de facto finite magnitudes, we've not yet clarified the nature of such magnitudes. So contextually, Aristotle spends a great deal of great effort proffering refutations for the Platonist and Pythagorean positions that mathematical objects exist separately from natural substances and intermediary between such substances and a domain of forms. So this is like one of the insights that we get into what exactly the Platonist with the capital P ontology is concerning mathematical objects. We get these sort of cryptic remarks by Aristotle in the metaphysics that they're positing intermediates. And the thought in the contemporary literature and in older literature as well is these can't amount to forms because we need to have a numerical plurality of them, all satisfying the same account. So it's very similar to part of the need for positing intelligible matter, you might think. But of course, these are going to be very different metaphysical systems. Okay, and they're in natural substances, respectively. Okay, so you might naturally infer that the domain of mathematical sciences must in fact be perceptible magnitudes themselves, but Aristotle proceeds to indicate that the mathematical sciences are not of the perceptible magnitudes per se, and yet not of any domain of objects separate from the perceptibles. So the solution is to implicitly use a reduplicative locution. So reduplicative locutions are locutions that reduplicate the subject term and qualify the term with respect to a gloss. So examples in Greek are like he, kathozon, ephozon, in Latin, in quantum, quatinus, qua. Some of these are implicitly reduplicative, so you don't have an explicit reduplication of the subject term, but grammatically speaking, they are reduplicative devices. And in English, we have like insofar as, to the extent that, etc. Right? So we were then able to claim that geometry is the special science of perceptible magnitudes. Not in quantum they are perceptible, but in quantum they are of some magnitudinal sort or other. Okay, so what exactly is this sort of gloss? So the way that I'll refer to this is the nominal that's qualified with respect to this reduplicative gloss, I'll just call the reduplicative base or the subject. And then the gloss is that phrase, that formula with respect to which the term is qualified. Okay, so what is the sort of gloss under which the perceptual objects, example perceptual magnitudes are to be considered from the standpoint of geometrical theorizing? Well, in the context of the metaphysics mu, Aristotle considers the following glosses. So in quantum, these perceptual magnitudes are lengths. In quantum, they are planes. In quantum, they are divisible. In quantum, they are divisible having position, etc. So this dovetails a little bit for the cognoscenti or people who are interested in some of the broader work that I do in contemporary analytic philosophy and mathematical logic. You can model this as a particular term-forming operator that takes as operands a pair of a subject and a formula in which the subject term features, or the term features more generally. And then, of course, logically speaking, these sorts of terms can feature in any term position in, say, a first order or second order logic, in general, in a higher order logic. And so then part of the project is you might be able to reformulate, this is one of the things I'm working on right now, reformulate, say, like Hilbert's first order theory of Euclidean geometry or Tarski's second order theory, just purely in a Aristotelian admissible way, right? Because you just have like these reduplicative operators. So just in this sort of in this theory. Okay, but you also might have more complex glosses. So in quantum X is triangular, and quantum X is isosceles, in quantum it's quantitative or continuous, etc. So these are mentioned in various places, including in the posterior analytics, but also in the metaphysics, as I had said before. So let me, just for the sake of time, make sure I'm getting through enough here. So one may speak of this triangle in the context of reasoning with a diagrammatic triangular inscription without presupposing it's being subject to change, as having certain metrical properties. That's the metrical properties we talked about. It's being perceptible. So when one's reasoning with this triangle, in this sort of setting, one's reasoning with X in quantum X is triangular. Okay, so you might assert this line is breadth, while considering the edge of a book B. And so part of the role this is going to have is an idealization role. So this is a very common objection. It's an objection that also arises in these sorts of discussions in early modern theories of mathematical ontologies. Um, so given that the relevant edge is not in fact breadthless, right, of a particular book, the proposition asserted was false. But on the Aristotelian view, reasoning with this line is not to reason with this edge of B, but rather with B's edge. In quantum, it is linear. And you might ask, like, well, why is it the case that that new suppositum, this new subject term, is going to be such that you aren't able to predicate some of the unidealized properties of the edge of the book? The point is, Aristotle talks about this more generally in the Sophistical Refutations 5. There's a particular fallacy of, called secundum quid ad simpliciter inference. So inferring from something that is qualified, some qualified subject term to the term simplicator. And that's exactly what you'd be doing, or vice versa. If you're going to say that some duplicative qualified term has all the same, true predicates as the unqualified term. Okay. So this central attribute is there's a metaphysically deep relation between geometrical objects and physical substances, guaranteeing that the range of possible geometrical objects is constrained by the range of possible physical substances. And so you can already see that, okay, if we can conclude something about the possible physical substances, then this might have certain constraints in our geometry. But the question is whether or not we can argue convincingly, deductively, that the constraints are interesting in a mathematical sense. Okay, so this provides a solution to now long-standing difficulties that moderate realists, that abstractionist theories of mathematical objects face, including the ideality of geometrical abstracta. I talked about that a little bit. Despite the non-ideality of geometrical abstrahenda, those things from which the abstracta are abstracted, the immutability and necessity of geometrical truths, right, despite the mutability and contingency of geometrical abstrahenda, the relative magnitudinal and positional properties of geometrical abstracta, even though geometrical aphoresis involves abstraction from the absolute metrical properties of abstrahenda. This last point, in part, dovetails with some of the things that Andrew was saying earlier concerning intelligible matter. In Aristotle, I see not only that the intelligible matter is important for the individuation of particular geometrical objects, but also for Aristotle, the notion of thesis, position, or place is extraordinarily important in geometrical configurations. And so if one is interpreting the intelligible matter to be something like the abstract, geometrical space, ultimately, that's the role that it plays, in a geometrical configuration, then you'll be able to, ground these sorts of properties. Okay, so how do we get finitism then? Well, so in the physics gamma, in the context of discussions of the perceptible infinite, apeiron, Aristotle famously distinguishes between the infinite in potentia, duname, and the infinite in actu, entelecheia, where both at least divide, at least in an account, into the infinite with respect to addition, to division, to plurality, and to time. So we'll be considering addition. So roughly the infinite by addition in potentia is a possibly implemented process whereby for some finite perceptible magnitude m, it is always possible by such a process to augment m to yield some strictly greater perceptible magnitude m prime. The infinite by addition in actu is the objectual completion of such a process. So the object that's yielded by the completion of some such process. Okay, so you might have noticed, right, if you've done enough calculus with convergent series, that there is going to be definite and indefinite addition. So what you might do is you might add such that there's always going to be a limit to the resultant object, right? So the summands will be such that the infinite sum will converge, right, to use anachronistic terminology. So that's what's called definite addition. Indefinite addition is an addition that will be such that given enough steps, it will exceed every magnitude. For any given magnitude, in other words, I should make sure I have the quantification in the right place with the right scope. For any given magnitude, for any fixed magnitude, for indefinite addition, there will be a place in the process where the resultant object exceeds that magnitude, that fixed magnitude. Okay, so we'll briefly gloss the first and principal argument in De Caelo, in particular 1.5 for the fixed finitude of the cosmos, which in turn entails the impossibility of its changing shape or size, and thus the impossibility of an infinite perceptible magnitude in actu. Okay. So this would have been interesting. It's interesting to try to compare this, I think, with some of the considerations that Martina was giving earlier concerning Aristotle and infinite processes. In part because we have so Aristotle here is reasoning counterpossibly. So he's reasoning by reductio that the celestial sphere, the outermost celestial sphere, is of an infinite distance from the center of the world. And then he's reasoning about the traversal of infinite processes that, although infinite, will be bounded. So in the language of transfinite set theory or ordinals, it's going to be such that there's a bound or last element to this sort of process, even if the process itself is infinite. So I just wanted to say that for people who want to compare with the earlier presentation. Okay, so consider an infinite circular rotating body about a point P1. So P1 is the center of the universe, right? Okay. The infinite circular rotating body is the outermost celestial sphere. P2 and P3 are distinct but arbitrary points on the outer limit of the body and collinear along this dimension of rotation. Right? Okay. So P2 and P3 can be said to be undergoing locomotion circularly with respect to P1. So ex hypothesis, the radii described by considering P1, P2, and P1, P3 are infinite in magnitude. Okay, it's infinite distance from P2 and 3 to the center of the universe. But then for any finite magnitude m, we may move sufficiently far along either P1, P2, or P1, P3 away from the center, such that the shortest distance between these two lines will exceed any given magnitude, right? Magnitude m. So what follows from this is that the arc length which must exceed each such minimum is going to exceed every magnitude, and so it'll be infinite. But since the heavens rotate fully in a finite time, it follows that an object embedded in a star or a part of the heaven moves from the place occupied by P2 to the place occupied by P3 in a finite time, and thus that the infinite is reversed in a finite time. Okay, what's interesting about this is, those who have, those who study Porphyry, who study Proclus will remember that Proclus takes as a suggestion from this sort of proof another axiom, the axiom that if you have two lines that intersect, then if you move far enough from their intersection point, then the minimum distance from any such point to the other line will exceed any given magnitude. That's exactly what's used here in this argument. Turns out that also is begging the question with respect to the fifth postulate. Okay, but I won't discuss that here. So Proclus proves postulate 5 using that. Okay, so we're exploring this conclusion to the physics gamma, and it follows that there can be no infinite in indefinite addition, in potentia, or in Act 2, right? Because you can't continually adding, you're going to hit the edge of the universe. Okay. So Aristotle immediately understands the potential corollaries that these metaphysical and physical results have an application to the standards of geometrical practice, and we'll consider this reasoning and the proposed reconciliation of the theories next. Okay, so so this is what he says in the Metaphysics Gamma. For whatever size the perceptible magnitude can be potentially, it can also be actively. So since no perceptible magnitude is unlimited, it is impossible to exceed every definite magnitude, for then there would be something greater than the heaven, right? So this is reasoning about the interchange of possibility and potentiality, which is a whole other topic in Aristotelian metaphysics. So this is the very famous passage right here, the Physics Gamma, about the reconciliation of this finitism with mathematical practice. So he says, our account, though in thus doing away with the active existence of an untraversable unlimited in the direction of increase, does not deprive the mathematicians of their theoretical knowledge. For even as things stand, they do not need the unlimited, since they make no use of it, but only that there should be a limited line of whatever length they wish. But another magnitude of any size you like can be divided in the same ratio as the greatest one can, so that, as regards proof at least, it makes no difference to them that its being among the magnitudes that actually exist is not necessary. Okay, so there have been a couple of interpretations of this passage. We have sort of classic interpretation by Tanaka and one by Hussey. And this is one in which there can be a vertical scaling down to a similar geometrical configuration for any geometrical configuration there is, right? For any one of arbitrary size. Okay, and then there's this more recent work by Ugaglia, which is the thought that actually we need to interpret some of the constructive geometrical axioms in terms of extending lines and whatnot by definite addition as opposed to indefinite addition. So the thought is that you have to extend them such that the successive extensions will be a convergent series. Okay. So you should note that this proposal also requires downscaling, but you need to downscale to smaller than the radius of the cosmos, and then you take half of that, and then you have your geometrical configuration. So that's what that requires. So they both require downscaling. So while both solutions avoid the possibility of needing to extend geometrical figures beyond the finite bound of the cosmos, the Hussey-Hintaka interpretation, I think, fits more naturally with the text of Physics Gamma, in which there is no indication that the more complex procedure of definite addition is in play. And secondly, the definite addition interpretation immediately encounters rather unpalatable consequences for the Aristotelian. So first, the geometers would need to systematically modify their mathematical practice, in which linear extensions often more than double the size of the original geometrical figure. They would be forced to accept highly unintuitive properties of parallels, right? So the Posidonius definition of parallels of equidistant lines would come apart from the definition that you see in Euclid of non-intersecting lines when extended indefinitely and whatnot. And so what you get is effectively a Lobachevskian geometry. And so Ugaglia is explicit that it sort of resembles the Poincare disk. Okay, so this would also be a non-Archimedean geometry. So it'd be very strange, I think, if Aristotle, in fact, was committed to a in non-Euclidean, non-Archimedean geometry. Now, you might think that like what you might think at first before this talk, hopefully I'll be convincing enough, is that he's not going to be formally committed just in virtue of his mathematical ontology to Euclidean Archimedean geometry. But then I'll try to argue that in fact is the case. He's formally committed to that. Okay, so we ought to examine this downscaling theory, right? The Hussey-Hintiga interpretation, which is prima facie plausible in the context of clarifications made concerning Aristotelian geometrical abstracta in section 2. And it's clear that it requires some important revisions. So first, we argued that in a reduplicative abstraction from perceptual particulars, geometrical abstracta are abstracted from the absolute metrical properties of their abstrahenda, so leaving only information of proportion and orientation. So that's important. So for concrete, let's to see what this criticism amounts to, let's take the example that worried the Aristotelian commentators. So in particular, Alexander of Aphrodisias. So consider Euclid 1.1. We've referenced it many times today, right? The construction of an equilateral triangle over a segment. And say we construct this equilateral triangle over the perceptible diameter of the universe. So suppose the geometer thus begins by asking us to consider d in quantum d is linear, d being the diameter, the perceptible diameter of the cosmos. Now he will, of course, wish to extend the geometrical configuration as posited, right, to construct some circles. For the moment, it includes only a single line segment. But to do so, he can do one of two things. So what he might do is he might try to reduplicatively abstract from other material particulars standing in some relation to d, right? So for instance, although this is not relevant to Euclid 1.1, he might consider another perceptible diameter of the cosmos, d prime, coplanar and perpendicular to d, coplanar with and perpendicular to d. And then the geometrical configuration, including d in quantum d is linear and d prime in quantum d prime is linear, would simply be a pair of perpendicular, co-bisecting equal line segments in the abstract plane. However, more plausibly, if the Aristotelian conception is to fit with geometrical practice, he might also simply begin manipulating the representation of the geometrical configuration as stated, the way that you do when you're reasoning about Euclid 1.1, right? D itself sort of falls away, right? It's constructing a pair of overlapping circles over the line segment. So as discussed in section 2, in so doing, he has ipso facto ceased to reason about d in quantum d is linear and is now treating the geometrical objects, including the original line, as separate. This is exactly as Aristotle says. In his geometrical procedure, he is only presupposing, if he's a good Aristotelian, that there is some physical configuration of abstrahenda realizing the configuration of abstracta represented. So this is what Aristotle says about the geometers treating the objects as though they are separate when in fact they're not. So in geometrical practice, if you're constructing a geometrical diagram, and there's been work on this where you're not going to do the full diagram, otherwise you'd be constructing like hundreds of circles for even like relatively trivial theorems, right? You reason in shorthand, and then if you're a good Aristotelian, you're going to want to say that whatever results from the geometrical configuration will have geometrical content. So there will be some configuration of abstrahenda in the world that realize that geometrical structure by abstraction. Okay. So of course, in the case of Euclid 1.1, if the geometer proceeds with 2, that is the second option, what I take to be the better option, then the relevant realization of the configuration will not feature D, but rather some collection of objects smaller than D. In the case of, right, because otherwise like you wouldn't be able to fit the abstrahenda for the configuration in the observable universe, or in the universe implicator. Thus, in the case of Euclid 1.1, the geometer must proceed with 2 if the starting configuration is D and quantum D is linear, remember D being the perceptible diameter of the universe, for there are simply no perceptible particulars from which to abstract the circles the geometer needs to stand in an encompassing relation in the abstract geometrical configuration to D and quantum D is linear. So this might be described as a sort of scaling, since the realization of the new geometrical configuration will be geometrically similar to, but smaller. It'll correspond to similar but smaller physical particulars than the original configuration, but it's not a scaling of the diagram or of the abstract geometrical configuration in any sense of the term. Rather, it's simply guaranteed, if the construction rules are valid, that there is some perceptible realization of the abstract geometrical configuration, where in many cases the abstrahenda composing such a realization will be similar. Okay, so how do we get from this to monism? So recall postulate 5 in Euclid that if a straight line falling on two straight lines make the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. Okay, so Hussey wants to say that, okay, maybe we can have a finitary sort of version of this. You might know that the triangle postulate, Euclid 132, that the interior angles of a triangle sum to two right angles is equivalent to the parallel postulate. So that's going to be a finitary sort of statement. It doesn't require you to extend lines indefinitely. So you might posit that. But actually, we can prove Sacchieri's postulate, right, which is equivalent in absolute geometry to the fifth postulate, using the meta theory of the geometrical ontology that we've talked about. So I'm using proof in not the object theoretic sense here. Okay, we're working with sort of metaphysical reasoning, but it's still going to be deductive, given what we said. So it should be clear that the traditional downscaling interpretations of Aristotelian geometry entail SP, right? So if you have two similar incongruent triangles, right, it's going to be the case that if you have any triangle, you can produce trivially a similar but incongruent one just by downscaling that triangle for any finite way. Okay, so according to our interpretation given in section 3.2, though, it's not clear that SP follows yet. So first, one virtue of our interpretation is that it's not explicitly positing an extra geometrical rule, augmenting classical geometry. So it's not our interpretation. As we saw, since the relevant downscaling, if it can be best called that, was only an application to the perceptible bodies realizing a geometrical configuration rather than applying to the abstract configuration itself, it's not actually clear that Sacchieri's postulate would follow at all. But in fact, we can show that it follows. So here's the argument. So as you might expect, you're moving between the object and the meta theory. So simply consider some constructible triangle, including according to Euclid 1.1. So we can do that in absolute geometry. We don't need the theory of parallels for that. Realize somewhere perceptibly in the cosmos. Okay, call the perceptible triangle T1 and its abstract correlate T2. That is T1. T2 is just T1. I used a quatenus here. Like in quantum, T1 is triangular. Okay. All right. Then extend the line forming one base of T2. So you form an external angle explicitly, and continue extending the line until, if the configuration were still implemented to be an abstraction from T1, there would be a body extending beyond the edge of the world in virtue of that line. Okay, so by Aristotle's solution to the physics gamma, the new configuration must have some perceptible realization, but notice that whatever such a realization is, the abstrahendum corresponding to the configuration's constituent triangle must be smaller, because these are proportion-preserving abstractions, and thus incongruent, but similar to T1. So call such a perceptible triangle T3, but then we may simply perform Aristotelian abstraction on both T1 and T3, in other words, on their bases, yielding an abstract geometrical configuration in which there are two similar but incongruent triangles, as the proportions between T1 and T3 will be preserved in the abstraction. Okay, so thus SP follows. And this is equivalent to the fifth postulate. So now there's like the serious choice points. Okay, like how exactly are we accommodating this? Are we claiming that there should be a new construction rule, or that there's some rule in general about what the physical particulars are on which we can abstract into a geometrical configuration or whatnot? And I simply think that these are going to be underdetermined by the textual data, right? So we're already talking about like some consequence of what Aristotle in fact says. And so if we're trying to think about how exactly to accommodate that formally by our contemporary rigorous standards into a geometrical theory, it's not going to make sense. We'll no longer be interpreting Aristotle. Okay, so we're not going to take a stand on that. So we must content ourselves in discovering a rather interesting corollary of what might seem to be an innocuous principle, that there's a quasi-informal sense that we've identified according to which Aristotelian geometry is Euclidean, and that is the sense in which we assert that it is. Okay, now because remember, monism is just the view that there's one true geometry. Okay, so Aristotle takes one condition for geometry as a special science to be its reasoning over domain of geometrical objects. And otherwise, it's empty syntax or empty construction procedures. And because the only possible domains for such objects are Euclidean, as we've showed, it follows for Aristotle that Euclidean geometry is the uniquely true geometrical science. Of course, he does grant himself geometrical reductio arguments, right, as we looked at in De Caelo 1.5. Okay, so the conclusion is just that the discussion highlights the surprising theoretical commitment that can be wrought by certain moderate realist doctrines of mathematical ontology and about theories of mathematical ontology more generally. In particular, such ontologies may constrain in interesting and surprising ways with deductive force, right? The possible mathematical theories, and leave but one admissible mathematical theory, and thus may constitute an argument for mathematical monism. So secondarily, to highlight a fascinating historical example in which a metatheoretical interpretation of the object theory can, if regimented and taken holistically, fix particular object theoretic truths to the exclusion of others. Thanks.
All right. Thank you very much, Jonathan. So that was a lot to put down the gullet. I'm glad that I watched your other presentation first, and now I'm wishing I might have to watch it again at slower speed. But that's not your fault. That's just I'm a little bit slow. But anyway, but yeah. Anyway, so what? Who wants to get in on a question? Yeah, Brother Christopher.
Yeah, so fascinating presentation. It was a little quick. So I guess my question is, um, do you think that Aristotle would, like a sort of a hypothetical Aristotle today who's been caught up on all modern mathematics would say, ah, yes, that is what I meant. Yes, I'm committed to geometrical monism. That's that's how I thought the world was or world is. There's just the one geometry. Or do you think there's space in his broader philosophical framework to say, well, actually, I'm kind of open um, to broader geometries. I mean, my position would be that no, he would probably agree with take the first stance to say yes. I'm not a Platonist. I don't want to countenance all sorts of speculative possible geometries, Euclidean. Like, what happens if you fifth postulate's not true? Nothing, because it's true. So, what's your thoughts?
Yeah, thanks. This is a great question. So the first thing I think you would say is that yeah, and part of this is speculative because it's textually underdetermined, is that I think, yeah, he would definitely think that the fifth postulate is true. He might himself be surprised that, in fact, it's being true just follows from his astronomical and kinematic finitism. So that's like sort of this interesting result where, like, just given his geometrical ontology, this just happens to be a corollary of his finitism about, astronomy and about kinematics. And then that's good news for him because he thinks that's true anyway. Because so he might be updated, and we've found out that in fact it's independent of absolute geometry, and that you can have Lobachevskian and elliptical geometries, but those will be precluded as not strictly being geometrical sciences just on the basis of their failing to correspond to geometrical objects in the admissible ontology that he gives. So I think I agree with you. And I think you'd be happy that this corollary, in fact, is
Mhm.
there, even if it wasn't live to him.
And it seems to me, I think he'd be surprised if it were the other way around, right? I think
Yeah,
he'd be surprised to be told, "Oh, it turns out your understanding of geometry is underdetermined by the world."
right.
Yeah,
Oh yeah, for
yeah.
sure. Or even like a more radical, a more radical converse would be the Ugagli interpretation, where it's going to turn out that he's committed to a non-Archimedean, non-Euclidean geometry in virtue of his.
Oh,
Right. So that there are these interpretations
mhm,
out there which I
mhm.
think really do violence to the geometrical intuitions that I
Yep.
mean, yeah, I mean that's why it was an open question whether or not postulate 5 was provable from the postulates of absolute geometry. Um, it wasn't it didn't seem to be on like worse slightly worse epistemic footing, but it didn't seem clear that it was like independent or some new contribution beyond the first four postulates.
Mhm.
All right, Andrew.
That was insane. I've never heard a ton of those things before. Um, where is the scaling down text?
The Aristotelian texts or the interpretive texts?
Aristotelian.
So that is a interpretation of it's a pretty speculative interpretation of this passage in the Metaphysics Gamma. Um, so let's see, way back here, this one. So the Gamma 7. So the thought is
Okay.
that because they don't care about the absolute metrical, so this is definitely reading into the text. That's why this is a controversial text. The thought is because the geometers don't really care about the absolute metrical properties of the largest line they're considering in a geometrical configuration, then you can just interpret that as small as you like among the physical perceptibles. That's the thought. And so
Yeah.
what you can do is you can just, if you don't care about metrical properties, then yeah, you can just scale geometrical configurations as you see fit, because that is in no way is going to transgress the subject matter of geometry. Yeah.
Yeah, made sense to me. Um, do you think that this is kind of Father Wetzel's question in a new way, maybe? Do you think that if Aristotle was confronted with the knowledge that things don't act according to the fifth postulate in the world, um, he might just say, oh shoot, I have to make a new rule. Never mind. When you're doing geometry, you do have to be careful that you don't make anything too big.
Yeah.
The scaling down is this thing about making the same thing and making a smaller thing with the same ratio. It doesn't work. I'm sorry.
Yeah.
There's actually rules for geometry. Is that possible, or are you saying no, you would never say that?
It's another really great question. So, one thing important to note again is just that this is entailed by you have to appeal to his finitism in astronomy and also like his kinematic finitism in order to get this result, this entailment result. So, if he's willing to say to grant to the contemporary physicists that it might be the case that we live in an infinite flat space, then it might not strictly follow. So that might give some leeway. But I suppose like the one thing I'll say is that it's not actually uncontroversial in the philosophy of physics and in the philosophy of science that the best physical theory, all things considered, is one in which we have a pseudo-Riemannian manifold. So there are interpretations of general and special relativity where you have what is called like Lorentz contraction of objects embedded in space as opposed to curvature, non-trivial curvature on the space itself. And those will be empirically equivalent. There's no physical experiment that will separate these neo-Lorentzian theories. Lorentz, who formulated the Lorentz contraction, this was his view to understand the Michelson-Morley experiment. So this is like sort of the first sort of ways of trying to understand how the world could be with the experiments that motivated special relativity. So just the thought is that you could have these physical theories where you have a totally flat space, but you just have systematic length contraction, Lorentz contraction, satisfying the Lorentz contraction equations of objects when those objects are moving in certain inertial reference frames or in certain gravitational fields. But the space is flat, the thought is. Okay. And the reason why general relativity is a much more popular theory and neo-Lorentzianism is heretical is like some of it is sociological, but also some of it is just that some people think it's a more parsimonious theory where you don't have systematic contraction of objects, but rather you just have a curvature on space-time itself. So Aristotle should resist, right? That it's just absolutely clear that our best physical theories tell us that a pseudo-Riemannian four manifold is in fact the real substantival spatial structure of the world. That's another assumption, right? If you even talking about like four manifolds, it's sort of to talk of space-time in a more substantival way. Of course, there are relationalist ways in which you can interpret that, but you have to do some work to do so.
Thank you.
Yeah, go ahead, Andrew.
Thanks. Um, so I guess this passage suggests this, but I had no idea that Aristotle believed that, am I understanding this right? Aristotle actually believes that there's something of the shape out in the world for everything you construct in geometry?
I don't think so. There are a couple of ways to go, and I think again it's textually undetermined. I don't think that he would say that there's something in Act Two. So there might be something in potentia. So it's very similar to some early modern theories. So for instance, Isaac Barrow, who taught Newton, he had this sort of view where he was a plenum theorist, so he was an anatomist, and he thought that any region of matter was such that it potentially encoded every geometrical configuration, no matter how complex the configuration is. And you might think that if every configuration is finite, then that's plausible, right? It exists in potentia. If you have this view where it exists in Act Two for every such possible geometrical configuration, then you'll have to go against the orthodoxy, take the minority view that there can be absolutely infinite pluralities in Aristotle. Um, it's a minority view because it requires you to say that. So, like, if you want some reading on who defends this view, for instance, like Jacob Rosen at the University of Pittsburgh defends it. And what's surprising about the view is it's not that textually, it's not that easy textually to refute. So what he says is that the commentators, modern and ancient, have confused Aristotle denying that there are infinite numbers with that there are no with his denying that there are infinite pluralities. So arithmos versus plethos. So the thought is that he never denies that there are infinite pluralities, only infinite numbers. So then you have to take that sort of view if you want to say that there are these things in Act Two, because the space of potential geometrical configurations, of course, is infinite. If you just think about all the potential geometrical configurations. So if you think that they all exist in Act Two, then you're going to have to say that there are infinitely many objects where that infinity is not going to be or that domain of objects is not going to be a number of objects, but a plurality of objects.
Thank you very much.
All right. Well, I think we are about out of time. So thank you, Jonathan Tanaka, for taking us all the way to the West Coast and closing off our spree across the time zones. Um, and yeah, thanks to everyone who stuck through it all day. I'll try to get the videos up on YouTube relatively soon. And then we can watch them at whatever pace we like. And I'll let you know when I've done that. So thank you all so much for coming out, and really appreciate it. If there's anybody watching along who has a paper you'd like to get in the next version of this, I make no promises for when the next time will happen. It could be next year, it could not be. But please feel free to hit me up. Always looking to feature new voices as you saw today. So thanks everyone so much.
Thank you, Ryan, for organizing it. You did a great job.
Yes. Thank you so
Yeah,
much.
thanks so much, Ryan, and everyone else.